I mean, you can get solid state to work, but the materials that you use are very, very expensive. You're talking 5 or 6 times more expensive than the materials that go into lithium-ion battery. If you look at the West versus China in the battery technology area, unless you own or make the active materials locally, you really haven't got control of your battery industries.
Which we're beginning to understand.
So there's been 5 fundamental revolutions in battery technology in the last 250 years. So my bet is the next one's not going to happen by next Tuesday and probably won't happen in the next 10 years.
Really? Hello and welcome to Beyond the Battery, a new series from EV Battery Solutions, where we chat with industry experts about the biggest EV topics shaping the industry today. I'm your host, Erin Baker, and each episode I'll be joined by a different leader from the world of automotive and electrification. This week, I'm delighted to welcome Isobel Sheldon, CEO at Western Cam and all-round battery expert. We'll be talking about the exciting and ever-changing world of battery technology, including what the future could look like. Thank you for tuning in. Let's get into it. Hi, Isobel.
Hi,
How
thank
are
you for the
you?
invite. I'm fine, thank you.
Good. Right, let's dive in with you, my favourite topic. Could you begin by giving us an overview of your role, what you're up to now, and how that came about?
So at the moment, I'm setting up a new company in the US. Pretty much, if you look at the West versus China in the battery technology area, unless you own the active materials or make the active materials locally, you really haven't got control of your battery industry. So,
Which we're beginning to understand, aren't we, to our cost in
yes,
Europe?
indeed,
Hmm.
indeed. And the cathode materials is a really, really important part of that. So we're setting up a cathode material manufacturing business in the US at the moment.
Can you just tell me what cathode material is for those of us who did English literature for a degree?
So basically, you've got two halves of a battery. You
Uh-huh.
have an anode and you have a cathode, and you have copper and aluminium foils that those materials are coated onto. And then they're either stacked or they're rolled up into a jelly roll and into a cylindrical cell. So you've got different types of chemistries, you've got different types of formats, but fundamentally, you have an anode and a cathode, and electrolytes and the separator are the main components of most battery technologies.
Hmm.
And we're focusing on the cathode material and in particular lithium iron phosphate, which is probably more commonly known as LFP,
Yeah.
which is the lower cost, more durable, long lasting of the lithium ion battery chemistries. And
That's
then
the
on
most common lithium ion. In terms of car batteries, that's kind of where most
Sort
people are at.
of. I mean, if you go back 4 or 5 years, what was called NMC or nickel manganese cobalt was much more common because it had a higher energy content, so your electric vehicle would go further. But of course, we've got this this emphasis on cost at the moment. So trying to get the cost of electric vehicles down so that when people go into car showrooms and buy them, they're paying a lower sticker price. So LFP is a much cheaper battery technology, but it
Right.
doesn't quite have the same energy density as the high nickel materials that have been commonplace over the last couple of years. So fundamentally, LFP is becoming about 55 to 60% of the lithium ion market at the moment.
Oh, okay. I thought it was higher. Right. Okay. And by density, t- for the consumer out there, that essentially means how far it can go on one charge.
Yeah, there's two ways of measuring it: volumetrically, so watt hours per liter, and gravimetrically, which is watt hours per kilo. And typically in the automotive world, it's a volumetric problem. You have a certain amount of space for a battery system,
Yeah.
so your volumetric energy density is really, really important. If you're putting a battery in an aircraft, it would be a gravimetric problem.
So you see, every day is a learning day. Excellent. Thank you very much. And that's batteries covered, right? We're done with that. Back to you. How have you ended up on this couch?
Well, it's been quite a journey for me over a very, very long period of time, about 47 years, in fact.
Which is my
Um,
precise age.
Oh, there you go. It's, sort of showing your age a bit. Um, I'm certainly a bit older than that, so
You
I've
don't
got
look it.
nothing to shout about. Chemistry is one thing that I've become familiar with, during my career in the battery industry, but also designing and manufacturing cells has been part of my history. Designing battery systems has been part of my history as well. So I've gone soup to nuts, if you like, from chemistry all the way up to vehicle level applications. But fundamentally, where I started was right back in 1978. I was 8 years old, and my dad was fixing his Mark III Cortina because, in those days, cars needed fixing every 5 minutes, and,
Mhm.
I think he was replacing the camshaft. And he finally got the engine built, rebuilt and put back together, got it winched into the car and connected all the fuel lines and all the electrical components, and, eventually fired it up, and I happened to be stood at the back of the car. And I could see the exhaust gases coming out of the exhaust pipe. Now, being an RAF brat and growing up on air bases, I knew fundamentally how aircraft flew. It was exhaust coming out of the back, pushed them along. So I said to my dad, is that how a car moves? The exhaust gases, do they push the car along? And he went, well, no, 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 and explained how an internal combustion engine worked. How we're taking the air that we breathe, mixing it with fuel, creating an explosion, which was pushing down a piston and turning a crankshaft and through the gearbox and through the differential at the back to the wheels. But be careful of those exhaust gases because they're toxic, not very good for you. And that's when it struck me. I was 8 years old and I thought, well, how mad is that? We're not going to have enough air to breathe in the future. Slight naive take on it. But fundamentally, taking the air that we breathe and creating gases that we can't breathe didn't seem like a very good idea.
Mhm.
So, in my head, it was, how mad is that? There's got to be a better way.
Out of the
And
mouth of
that's
babes. Yeah.
47 years worth of careers come off the back of that.
And so what did you I'm interested in what you did for A level or university and how you then got into it because, there is still a big thing for automotive and all the supplier wider industries around automotive, around women and STEM. We haven't got, we haven't got wide enough pipelines. We haven't got senior enough women throughout the industry. So what got you from education through higher education to a career?
Fundamentally, it didn't. So I left school at 16.
Right.
And I went and joined an apprenticeship in the defence electronics industry. I went to work for Marconi in Lincoln. And that was at the back end of the 1980s. And when the defence cutbacks came in after the first Gulf War, pretty much a lot of people were losing their jobs
Mhm.
within defence electronics because you had two choices. You either went into communications or you went and found a job somewhere else. So I went and found a job somewhere else, which was working in an engine factory, which I did for 4 years.
Mhm.
And that's when I decided that I wasn't going to do that for the rest of my life. So I blagged my way into a drawing office and design office for construction equipment and mining equipment. And learned mechanical engineering, electrical engineering, hydraulics, was pretty much self-taught in most of those
So learned it
things.
on the job.
Learned it on the job, but was mentored by engineers in those departments. And that led to a career in sales, ultimately in the automotive industry. And I ended up working right around the world. I was responsible for the four Japanese manufacturers in Japan, the whole of Sweden, Ford in the UK, and Ford in the US as well.
I mean, a prof, aren't you?
Yes, well, it's honorary.
Is it?
Yeah. It really stems back to the work that I've done in battery technology because when I started in battery technology as a professional career back in 2002, 2003, you couldn't go to university and learn these things. It was pretty much an undiscovered country, if you like, as
Mm.
far as taking lithium ion cells and putting them into battery packs was concerned. So I was pretty much one of the first people that put lithium ion cells into vehicles and got them onto the road. And the inspiration for that particular part of it came when I was in Toyota's technical center in Nagoya in Japan, because they're a customer of mine. And I was looking at the first generation of Toyota Prius as a hybrid system, nickel metal hydride batteries, no charger, it was not plug-in. And that's where I had the inspiration to convert hybrid electric vehicles into plug-in hybrid electric vehicles and left my very well-paid job with the automotive industry, bought a second generation Toyota Prius, and then worked with a company in California called NGCS that no longer exists, to do the first plug-in hybrid conversions of the Toyota Prius. So that's my claim to fame
Wow.
is I made
That's a massive
first
claim
first
to
commercially
fame.
available plug-in hybrid in the world was pretty much my work.
I've known you for a bit, and I'm not sure I knew that. That's how humble and brilliant you are. Oh, this is just turning into a one-person fan club here. All right, let's try and get back to some questions. So, you've been in the battery space since the early days, as you've just amply demonstrated. Talk us to we mentioned lithium ion, but some idea of the battery technologies you've been involved with. Are there many, many out there that are never going to see the light of day that we don't know about? Are there, you know, four in contention right now that you would say they're all in contention to play a part in mass transportation? Where are we with? different sorts of battery technologies?
So I think it's, we have to put a bit of context into these
Please do.
next, game-changing technologies that are supposed to come along by next Tuesday.
Yeah,
Most of them won't.
right,
So there's been five fundamental revolutions in battery technology in the last 250 years.
right.
So you've got the voltaic pile, which is the original battery technology that was created by Volta. You've then got lead acid batteries. So lead acid plates and sulfuric acid. The kind of technology that's been powering, since the industrial revolution, since steam power generators were invented. Because lead acid battery technology was invented for a while, but it couldn't be used because we had no method of charging it until the steam power generator came along. And then fast forward about 120 years, nickel cadmium batteries come along.
So when are we
So we're
talking?
talking about 1930s,
Okay.
1940s. And pretty much that became the technology of choice as far as rechargeable batteries for portable electronics was concerned for the next 4 or 5 decades, until nickel metal hydride came along in the 1970s and 1980s. And then that became the lighter weight version of nickel cadmium batteries. And of course, cadmium is a health hazard. It's a heavy metal. It's a metal, once it gets into your body, it never leaves again. So to move away from NiCad to nickel metal hydride was a real big plus for the environment, and led to the nickel cadmium battery ban in the early 2000s. And then as you come into the 90s, lithium ion came along. And fundamentally, that is all there is for the last 250 years as far as battery revolutions is concerned. So my bet is the next one's not going to happen by next Tuesday, and probably won't happen in the next 10 years.
Really
Mm.
interesting, because everyone keeps talking about solid state batteries, and they throw the term out there, and then media grab hold of it. Oh, solid state batteries, they're here, they're just around the corner.
It's going to revolutionize the world by
Yeah,
next week.
yeah.
Yeah, I mean, this technology has actually been around for a long time. You will talk to battery scientists that have been working on solid state chemistry for 20 years.
Could you just explain solid state chemistry?
So,
Words of one syllable.
solid state, right. So, a normal lithium ion battery has a liquid electrolyte. So, remember we talked about the anode and the cathode and the separator earlier on?
Yep.
Well, in between those two things is an electrolyte, which allows ions to move backwards and forwards between the anode and the cathode, whilst the electrons are going around the external circuit, which is your drive circuit in your electric vehicle,
Yep.
or could be the charger circuit, putting charge back into the battery. And I've really oversimplified that for very good reason,
Yes,
because it
that's
gets
fine.
quite
Yep.
complex.
Great. Thank you.
Um, but for solid state, you have fundamentally the same system. You have an anode and a cathode, but you don't have a liquid electrolyte, you have a solid electrolyte. And you would generally change the anode away from common material, which is graphite, maybe with some silicon at the moment, to a lithium metal anode, to take advantage of the fact that with the solid state battery technology, you haven't got a flammable electrolyte, and therefore, in theory, it's safer.
Right.
So you can put a more volatile anode against it, which would be a lithium metal anode. If you go and drop lithium into water, and it will start
Yeah.
to fizz and crackle and explode. So you've got to keep water away. But the problem with solid state battery technology is that with the liquid electrolyte, you wet out into the surface, so you have a lot of good connection between the anode material and the cathode material on the electrolyte, which allows the ionic transfer to moving to a solid surface, a flat surface that just abuts. And that surface chemistry is very, very difficult to get to work properly. And there are all sorts of problems, like as you're discharging the battery, you're stripping lithium off the lithium metal anode, and you're inserting it into the cathode material through that solid electrolyte, and that leaves voids. And then when you try to charge it back, it electroplates it onto the anode, and that tends to develop little peaks. And those little peaks can push through that solid electrolyte and cause short circuits. It's called dendrites.
Right.
So you end up with this real rapid failure over time, because the
Mm.
internal resistance goes up, because you haven't got as much surface area making contact.
Hmm.
You end up with these dendrites piercing through that solid electrolyte layer, and potentially could cause short circuits, which is a safety issue. And solid state batteries are supposed to be safer than lithium ion batteries and higher energy density.
So solid state batteries are supposed to be safer because presumably they're supposed to be less likely to catch fire.
Correct.
but we've got the issues that you highlighted. So,
Indeed.
is solid state still the goal if we can iron out those issues?
So, yes, fundamentally over the long term, absolutely. But the problem is, I mean, you can get solid state to work, but the materials that you use are very, very expensive. So, you're talking 5 or 6 times more expensive than the materials that go into a lithium ion battery.
And that is a big problem at the moment. We're trying to get
We're trying to
electric
get
car
the costs
prices down.
down.
Yeah,
And the other problem is that nobody has actually figured out how to make these cells cost effectively,
right.
as far as the manufacturing process is concerned. The manufacturing process is incredibly difficult.
And what about weight?
Weight should be better because lithium, you've got hydrogen, helium, lithium in the periodic table. So it's like the third lightest element. That's why we use it in lithium ion batteries. So if you're replacing graphite with lithium, you've got a much lighter material, and therefore your gravimetric and, in theory, your volumetric energy density should be better. But there is a problem. Solid state batteries need to work under a lot of pressure
Uh
to
huh.
get the surface chemistry to work
Uh huh.
because we haven't got a liquid in there, we've got a flat surface. So you've got to put a lot of mechanical structure around the battery pack to push the cells together to make them work properly.
Right.
And at the moment, that structure that you need to apply that pressure will pretty much offset the improvements in energy density that you'll get.
And what about the theoretical repairing and remanufacturing of solid state batteries compared with what we're up to now?
It really depends on how they get them into a pack. So
Mm.
once you've figured out the cost problem, once you've figured out the manufacturing problems,
Mm-hmm.
you've then got to design a battery pack. And we already know that the structure is going to be big to push them all together to
Mm-hmm.
make it work. Um, how those cells are going to cycle over time, what their degradation is going to look like, and what the in-service problems are going to look like over time, we have no idea at the moment. So the idea of even thinking about recovery and repair and refurbishment at some point in the future for a battery technology we don't even know how to implement at the moment is a bit of a stretch too far for the industry.
Very interesting. We're kind of in this nascent era, aren't we, of electrification and everything that means for consumers, but everything it means for technology and for manufacturing and all of it. And while we're trying to figure that out, people keep throwing new ideas into the pot, like solid state batteries are just around the corner, or hydrogen. It's all about hydrogen over
Or
here. Stop
sodium
looking
ion
electric.
or something else. Yeah,
Yeah,
there's
yeah,
always something that comes along. Really, fundamentally, what we've got to do is we've got to focus on making sure that these electric vehicles are cost effective enough to put into the hands of more people.
yeah.
And that means focusing on making current battery technology cheaper.
Cheaper. Yes. Well, speaking of which, so let's go back. Ditch solid state, forgotten about. Let's go back to current lithium ion tech. Let's look at the three main barriers or concerns for consumers and uptake. The barriers to uptake: reliability, range, performance. Where we are now today, in 2025, have we pretty much reached the limit of batteries in these areas, or is there more to unlock with the current technology we have around reliability, performance, range, and battery degradation? Let's say.
There's never going to be one size fits all answer to all of those questions. So it pretty much depends what you want the vehicle to do. So if you need a vehicle that needs to go long distances, you're going to need to choose the chemistry like NMC, nickel manganese cobalt, which has a high energy density, so you can get a lot of charge capacity into a very, very small space. Therefore, you can make your electric vehicle go as far as you possibly can. And typically, 350 to 400 miles
Mm,
on a WLTP cycle is pretty common these days,
yeah,
or becoming more common. Um, and that's going to depend on how you drive the vehicle, what the temperature in the environment you're driving it in is.
yeah,
So in winter, you end up with a degradation of battery performance. In summer, it's a lot better, but you end up with the air conditioning running. All of these factors come into the decision matrix that you make when you design a vehicle to say, what is it I want this vehicle to be able to do?
hmm,
So premium vehicles are pretty much going to stick with the high nickel chemistries. The problem with the high nickel chemistries is the cycle life is fairly short. So about 1,000, 1,200 cycles, full 100% depth of discharge cycles is typical for a modern NMC type battery technology.
Right.
But the thing is, you never discharge your vehicle 100% every single day.
No.
You do that a tiny, tiny amount of the time.
Yeah.
So you're typically going to be using 15 to 20% is the consumption of a total charge per daily cycle. Therefore, if you add up all those shallower cycles, you end up with a battery life that's going to be sort of 12, 14 years before it gets to 80% of its original capacity.
Mhm.
But those vehicles are always going to be fairly expensive. There's always going to be a price differential. So to come across as something like LFP, which gives you a cheaper solution, and you see that in things like the Renault 5. The urban version of the Renault 5 has an LFP battery because it doesn't need to go so far. It's not designed for long distances. It's designed for local trips, going shopping, taking the children to school, going out for your leisure activities locally at the weekend. Therefore, you can get away with a cheaper technology with lower energy density that's got less range.
Mhm.
The advantage with LFP, though, is the cycle life is significantly longer. So the durability is a lot is improved with that battery technology. It's about 4 times better cycle life compared to the high nickel
Wow.
materials. So you've always got these trade-offs that go on with the different chemistry solutions and the different vehicle requirements and the different missions you want these vehicles to do.
I mean, it sounds like under either of those circumstances, though, that the 8-year average industry warranty for a battery is more than enough to,
Oh yeah,
if you're saying that 10
indeed.
years should be fine for the more premium.
Or if you come back to when I started in electric vehicles back in the early 2000s, we had no idea how people were going to drive these vehicles. We didn't know if they were going to be driving them more because they would cost them less to run because they were running them off electricity and not petrol or gasoline. We didn't know if they would have less of a guilt about driving their vehicle because they knew they weren't creating all this pollution.
Yeah.
So we didn't really know how far people would be driving them if they would be at the same frequency that people drive internal combustion engines. I've recently seen that the distance per year that most electric vehicles is actually higher for
Yes.
internal combustion engine,
Yeah. I love that
compared.
stat. That's what
That's
our data's
great.
showing. Yeah.
But it just goes to prove that we were pretty right to be conservative with our engineering assumptions for battery technology because I've said that nickel manganese cobalt has 1,200 cycles. If you go back to some of the earlier versions of it, it had 3,000 cycles because we didn't know what the degradation was going to be versus how people were going to use their vehicles over
Right.
time.
And are you showing the very top level generic data that I've seen on the battery degradation? The performance drop off each year because consumers always say, well, if I buy a 3-year-old EV, is the battery going to be okay? Some of the early data that was coming out was showing 1 to 2% performance drop off a year, maybe. How does that strike you? Is that about right?
Seems probably slightly aggressive to me, from what I've seen across a 25-year career in this industry. Batteries have lasted far, far longer than we ever expected them to be.
Hmm.
And I think that we had a justifiable conservatism
Yeah.
back when we started this industry because we just simply didn't know. And the worst thing in the world was to make an assumption that fell short and batteries would fall over
Yeah. Sure.
prematurely. I don't think that would have been a good outcome.
No, you
But
need the confidence.
but certainly to be well overestimating as far as battery degradation is concerned, and then the reality to come in under those targets is exactly where the industry needed to be. Should give people confidence for second-hand electric vehicles.
Yeah. Yeah. Good. Um, Therefore, what areas of battery tech are you excited about at the moment?
Oh wow! I think I've probably been around long enough in this industry to see all the hype and see all the
Mm.
disappointments as far as, coming back to it's going to change the world by next Tuesday. 99% of what I read in the press is complete nonsense as
Don't say
far
that. I mean,
as
apart from everything I write,
but
obviously.
you
So,
review cars, not battery
okay, good.
technology. So, but you see these, go to the Daily Mail, go to the Mirror, go to the Telegraph, go to some of the other publications around the world, and you see an announcement about these scientists have uncovered this amazing battery technology that's going to change the way that we live and the way that we move around. 90% of it has probably got about 10 years to go in the lab
Mm,
before it even becomes a commercial reality. And then it's got 10 doors to go through,
mm,
and it's probably only gone through door 2.
mm. And it's
And
got to scale up at some
yeah,
point.
it's got to scale up. It's got to be proven. It could get to door 5 and fall over because there's some exotic material that's required that's really expensive, or some process that hasn't been quite invented to make it work. Coming back to the conversation about solid state battery technology, all those things are true about solid state. Great in theory, in practice and delivery, it's a lot more challenging.
So, anything you're excited about at the moment in battery tech that you can talk about?
My view at the moment is that we have battery technology that is just about right, I think. It serves the purpose.
I like it. You're
It means
decently
that we
conservative.
can we can go the distance we want, we can spend the money that we want and get the vehicles we want. Bear in mind that, compared to when I started, battery technology has doubled in its energy content.
Yeah. I mean, that
You
alone
know,
we should be
it's
extraordinarily
huge.
grateful for.
We've probably got another 10-15% to go on this current
Okay.
technology path.
Okay. Battery supply chains. How do you see the industry improving? Well, this is a big question. Sustainability, transparency, and localized sourcing. I mean, in some ways, those three are defined areas, but actually, in some ways, they all, it's a Venn diagram of the three of them, isn't it? One thing begets the next. I mean, my thing I'm interested in is sustainability, and localized sourcing comes into that.
I think sustainability is really important in the supply chain for battery technology. And the reason for that is that, what is the purpose of putting an electric vehicle on the road? It's to improve the pollution in our cities, it's to reduce CO2. So if we're not serving that purpose with a sustainable supply chain, it's a bit self-defeating. Now, you'll see an awful lot around LinkedIn, you see a lot in the press about how dirty the supply chain is for battery technology. In reality, it's not that bad. If you compare it with fossil fuels
Right,
and the amount
right.
of oil that's dug out of the ground and burnt every day, and that's a complete loss system. You can't recover any of those materials and get them back. The sustainability of the battery technology, the battery industry today is exceptional compared to the fossil fuel industry. Does that mean that we rest on our laurels and say, okay, we've done enough, this is good enough? No, I think we can always make improvements. And I think localization is a big part of that. At the moment, overwhelmingly, China dominates the battery material supply chain. That has to change moving forwards. And that's part of the reason why I'm doing what I'm doing now.
Yeah.
Um, because if you don't have control over the battery materials value chain, you don't have control of the battery industry, and you're always going to be dependent on one area of the world that's super dominant at the moment. So things need to move moving forwards. Otherwise, we've got a bit of a challenge on our hands.
Yeah. Speaking of what you're trying to do and get off the ground in the US at the moment, gigafactories. Why have you chosen America? Is the UK, are we beyond the point where we're going to attract gigafactory investment here?
One of the fundamental problems we have in Europe as a whole, and not typically just the United Kingdom, is our cost of energy. The battery industry is an energy intensive industry, and making the materials is particularly energy intensive. So if you've got a high cost of energy, it pretty much makes you uncompetitive. So we have to do something about the energy cost. And, as you know, I'm part of the Gigafactory Commission at the moment, and that's one of the elements that will be discussed and addressed over time. But today, for me to be able to set up a business and set one up that's going to be cost competitive with China, I have to go where the energy cost is lowest, and at the moment that is in the US. And certain areas in the US, the cost of energy is lower than it is in China. So because we're using very, very similar processes and very similar materials, it means that we can be one for one competitive with China on those materials, which
Wow.
is not something you often hear in the
No, it is
battery
very much
industry.
not. And remind me where you're setting up in the US?
We have two states under consideration at the moment.
Okay.
We're not announcing them yet,
Okay.
but both of them are low energy cost states.
And is that the primary driver for those two states?
Well, it's the main driver,
Yeah.
but the US as a whole has a pretty good uh, protection against Chinese competition.
Yeah. Yeah.
Chinese businesses are not welcome in the US as 100% owned entities. So either they have to develop a relationship with the local companies to get that technology across the line in the US, or companies like ours who already have the knowledge. And within our team, we have some of the people that invented LFP in the first place on our team. We already have that team in the US ready to go to start scaling this business up. So we don't have much competition in the US.
I'd invest if it's any consolation. I shall raid my son's piggy bank. Finally, if we fast forward to 2035, what do you think EV batteries will look like from today? I mean, it sounds to me like pretty similar to where we are at the moment.
Yeah, 15 to 20% improvement in energy density, I think, is where we're going to be. I
And
think
same drop in costs?
um, I think the costs will stay the same,
Okay.
maybe creep up a bit, but the energy density will get better.
Okay.
So, that's probably a lower cost per cell, but the dollars per kilowatt hour will probably creep up slightly from where it is at the moment because the materials are getting more expensive. We've got inflation to cope with. But if we can get that 20% improvement over time, then pretty much we'll have ticked all the boxes without having to go for exotic solutions like solid state.
Oh, Isabel, it's been an unalloyed joy and pleasure. Thank you so much for joining me.
Thank you for all the really good questions. I've really enjoyed this. It's been
Thank you.
wonderful. Thank you.
Thank you for watching. Please remember to like and share this episode and follow EV Battery Solutions Europe on LinkedIn and YouTube to keep up to date with the rest of the series.